So I'm now recording. Okay, let's get started. So major reminders. The final for this class, Math 231, is on December 21st from 8:30 p.m. to 10:30 p.m. Test 3 is on December 9th in class on Zoom. And the review for test 3 is today. So what chapters is on the test? So okay, so the chapters on test 3 are chapters 5, 6, 7, and 8. Okay, so if you look at the review sheet for test 3, the chapters there are the chapters on the exam. Okay, so Thursday is the last day of class. So I have to think about when I can meet with you to review for your final. So I would be willing to do it Thursday night after your final, so it would have to be very late because I also have another class and I'm giving them a review after this class for their final on Thursday. So let's talk about that a little later. So I really don't have much time, but okay, so these are the chapters on the exam. So let's go back to Word. Okay, so the final is on December 21st from 8:30 p.m. to 10:30 p.m. Reminder, test 3 is on December 9th in class on Zoom. The review for test 3 is today. Okay, so we had a lot of homework to do today that I assigned a week ago. So any questions about all that homework? Keep in mind I have an office hour tomorrow. So if you want to ask me questions about it then, I'd be happy to help you there individually also. So remember, there's an office hour tomorrow. So tomorrow night. Okay. Any questions about the homework? If not, I'm going to keep going. So we can come back to it possibly. Okay, I don't hear any questions. So I want to cover the material. 8.1, general linear transformation. So this is the first, we have left is chapter 8 now. So definition 1. If T is from V to W is a mapping from a vector space V to a vector space W, then T is the linear transformation from V to W if for all vectors U and V in capital V, and for all scalars K, T of KU equals K times T of U. And T of U plus V equals T of U plus T of V. Okay, so this is sometimes called the homogeneity property. You're just moving the constant from inside the parentheses to outside of it. And this is called the additivity property. It's T of U plus V equals T of U plus T of V. Okay, so if you have a mapping from one vector space to another, you call T a linear transformation if both 1 and 2 hold. So these two properties characterize a linear transformation. That's the name of it. Okay, if V equals W, if the domain equals a codomain, then T is called a linear operator on the vector space V. Okay, so the name linear operator, all that's doing is that in addition to being a linear transformation, satisfying these two properties, that is just mapping a space to itself. Okay, so linear operator is just a specific linear transformation where the domain and codomain are the same instead of different. Okay, and so again, so linear transformation is one in which 1 and 2 hold for that function. If you can show these two things hold for a T, then you call it a linear transformation. Okay, now if V1 to VR are in capital V and K1 to KR, are scalars, then you have the following. You have that T of 0 equals 0. And if you have that, then the following happens. Then you have T of K1 B1 plus K2 B2 plus ... plus KR BR is equal to K1 T of V1 plus K2 T of V2 plus ... plus KR plus KR T of VR. Okay. Okay, and so this is for a linear transformation, capital T. So for a linear transformation capital T, a function which has these two properties, if you take T of this, you can separate it into its separate sums, T of K V1 V1 plus T of K2 V2 plus dot 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 plus T of KR VR, and then you can pull the constants out of each of them and get this expression. Okay, and so this is equation 1 in this section. Okay, now theorem 8.1.1. Did I actually avoid this? Okay, so if T is a linear transformation from V W is a linear transformation, then the following holds. T of 0 equals 0, and T of U minus V is equal to T of U minus T of V for all U and V in capital V. So for all vectors U, little u and little v in capital V, you have this equation here. Okay. In fact, every matrix transformation T sub A from Rn to Rn, where the domain V is the domain, which is this Rn, and W is the codomain, which is that Rn. And the zero transformation T of V equals 0 for all V and V. These are linear transformations. So every matrix transformation is a linear transformation. The zero transformation is also a linear transformation. Okay. So every matrix transformation satisfies these two properties. That's what a linear transformation is. Okay. It's actually a matrix transformation if and only if linear transformation. So every linear transformation is a matrix transformation. And every matrix transformation is a linear transformation. Okay, fact. The identity operator on V, the map that sends V to itself, IV equals V, for all V in capital V is a linear transformation. Okay, so for this map, you have property 1 and property 2. Fact. If you have T from V to V given by T of X equals KX, this is a linear operator on V. Okay, so this one, T of X equals KX, also satisfies these two properties. Okay. So if this constant K is strictly between 0 and 1, T is called a contraction of V with factor K. And if this K is greater than 1, T is called the dilation of V with factor K. Okay, you can think of contractions in the sense getting smaller, and this for small k, and then for k larger than 1, you think of dilation as getting bigger, so you associate that with k greater than 1. Okay, so theorem 8.1.2. Let T from V to W be a linear transformation, where V is finite dimensional. If S equals that set is a basis for V, then the image of any vector little v and capital V can be expressed as this expression. So if you take T of V, where V1 to Vn is a basis, then you can think of V as being a linear combination of these VIs. Okay, so you could think of T of V as being equal to T of a linear combination of the VIs, which you would say is V. So V would be C1 V1 plus C2 V2 plus dot 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 plus C n Vn. And so taking T of that by our earlier observation, this is equal to C1 T of V1 plus C2 T of V2 plus dot 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 Cn T of Vn. Okay, and so that's how we get that. Saying that this is a basis means every vector in capital V can be expressed as a linear combination of them. So you can express V as being this linear combination of V1s to Vn's, and then you apply our last effect to that, and you get this equation 3. Okay. Example 10. Consider the basis S, which is V1, V2, V3 for R3, where V1 is 1, 1, 1, V2 is 1, 1, 0, and V3 is 1, 0, 0. Let T from R3 to R2 be the linear transformation for which T of V1 is equal to 1, 0, T of V2 is equal to 2, -1, and T of V3 is equal to 4, 3. find T of x1, x2, x3, and use the formula to find T of 2, -3, 5. Okay, so this is what you do. You take the 3 tuple x1, x2, x3 that you're inputting into T. You want to think of it as a linear combination of V1, V2, and V3. Okay, so this is V1, this is V2, and this is V3. So in order for this to be a linear combination of V1, V2, and V3, you're multiplying each of them by constants C1, C2, and C3 respectively, and adding the products and expressing X, that 3 tuple, as that sum of products. Okay, so you have x1, x2, x3 is equal to this linear combination. And so on both sides, you have 3 components. You have 3 components here. Then after you multiply and add, you'll get 1 3 tuple here. So you, by equating corresponding components, meaning the first component on this side is equal to the first component on that one, the second component on this equals the second component on that side, the third component on the left is equal to the third component on the right. You get the equation C1 plus C2 plus C3 equals x1, C1 plus C2 equals x2, and C1 equals x3, right? Because you see a C1 here, a C1 here, and a C1 there. That corresponds with the x1 here. That's how you get this equation. C1 plus C2 and 0. C1 plus C2 is equal to x2. And then here we have a C1. Well, the third component of a C1 plus 0 plus 0. So C1 is equal to x3. And that's how you get those 3 equations. If we have a linear system that you can solve for C1, C2, and C3, where x1, x2, and x3 are constants. So this yields this solution. C1 equals x3, C2 equals x2 minus x3, and C3 equals x1 minus x2. So now that you solve for the C's, you can now express this as a linear combination of V1, V2, and V3, where this is x3 is C1, x2 minus x3 is C2, and x1 minus x2 is C3. So you now have this as a linear combination, and then you just multiply and add components. Well, no, sorry, you just say x, you just substitute these vectors for V1, V2, and V3. So you get x3 V1 plus this times V2 times this times V3. So thus, if you take T of the left side, you could say it's equal to T of the right side. And so T of that thing that I'm bolding is x3 times T of V1 plus x2 minus x3 times T of V2 plus x1 minus x2 times T of V3. And we know what T of each of these vectors are. It says T of V1 is this, T of V2 is that, and T of V3 is that. Because we know the images under T of V1, V2, and V3, we substitute this, this, and this into this, this, and this correspondingly. And then we multiply and add, and we get this single 2 tuple here. This is a sum of 2 tuples, which gives you a single 2 tuple. So the image under T of this 3 tuple is this 2 tuple. T is a map from R3 to R2. It sends 3 tuples to 2 tuples. So if you input a 3 tuple, the output is a 2 tuple. Thus, if you want to calculate T of 2, -3, 5, you just set x1 equal to 2, x2 equal to -3, and x3 equals 5. And you plug those 3 numbers into those expressions, and you get the 2 tuple 9, 23. Okay, so the point was to find T of this, right? And so in order to do that, you're given these values of T. You want to express x1, x2, x3 as a linear combination of V1, V2, and V3, given this basis. So you're given a basis, so you express this as a linear combination of these 3 vectors. And when you do that, you could then take T of this, and it's equal to T of that linear combination, which again, I then got was equal to this, right? And then by substituting the given values of T, you now have T of that is equal to this. And now with that general expression, I found a specific value of T for a specific 3 tuple and got that answer. Okay, so that was the idea of that problem. Okay, so fact, D from V to W, the function that maps F into its derivative, or D of F is equal to F prime of X, is a linear transformation. So this map capital D is a map from one vector space V to another vector space W. Now, when you look at this, you see I'm inputting a function. So you can have vector spaces of functions. Like I said, vector spaces are more general than physics vectors, right? Physics vectors, you just have arrows and you add them or subtract them, right? Physics vectors are just arrows. But in math, vectors are anything that satisfies all 10 axioms for a vector space. And so it turns out that you can talk about a space of functions as satisfying all 10 axioms of a vector space. And so this map, linear map, maps each of those functions to its derivative. And this is a linear transformation because d of f plus g is equal to f plus g prime, which equals f prime plus g prime equals d of f plus d of g. So d of f plus g is equal to d of f plus d of g. And if I did d of kf, that would be the derivative of kf, which is k times the derivative of f, just k times d of f. So both those properties for a linear transformation hold for this map D. So D is a linear transformation. You can show the two properties of a linear transformation hold given this rule defining this map D. Okay, in definition 2, if T is from V to W is a linear transformation, then the set of vectors in V that T maps into 0 is called the kernel of T. Okay, so the kernel of T is the set of all inputs for this function whose output is 0. Okay, so it's all the things that you could plug into this function whose output would be 0. That's the kernel of T. And it's node by ker of T, like that. That's the denotion of it. It's a subset of the domain of all the vectors that T would map to 0. That's the kernel of T. The set of all vectors in W that are images under T of at least one vector in V is called the range of T, denoted by R of T. Okay, so to draw a picture of this, okay, so if you have a linear transformation T from its domain, which is, let's say, V, to W, which is its codomain, and this is T, and let's say we look specifically at the point 0, right? Let's think of the subset of V that T would map to 0. So all these guys. These are all the guys that will be mapped directly by T to 0. Okay? This is called the kernel of T, what I just defined. The kernel of T is the set of all inputs whose output is 0. So this pink set in the domain is the set of all vectors that T would map to the 0 vector in W. Now, let's say you have a bunch of vectors in W that are mapped to by things in the domain V. So let's say T would map this point here, and it would map this point here, and it would map this point here, right? And in general, it would take all of these things, right? It would take these guys, and it would map them to this set in W. Okay, where the pink subset would map specifically to 0, but these other orange points outside of the pink area would still map to other things in W, just in this pink region. Actually, wait, let me fix it. I want all the things inside the set, not just a subset, right? So all, if you're considering all the points in the domain, right? Okay, so considering all the points in the domain, not outside of the domain, just saying it, all the points in the domain. Well, let's say they only map to this orange region in the codomain, right? Then this set here, this set is called the range of T. It's all the vectors in W that are mapped to by at least one thing in the domain by T. Okay, that's called R of T. That's the range of your linear transformation. Okay, so the kernel of T is a subset of the domain, and the range of T is a subset of the codomain. Okay, so example 13, if T sub A is from Rn to Rm is multiplication by the m by n matrix A, then the kernel of T sub A is the null space of A, and the range of T sub A is the column space of A. Okay, so what does that mean? So multiplication by an m by n matrix A means you're taking a vector x Rn, You're taking a vector x in Rn and left multiplying it by A. Okay. And so that action of doing that. So now the null space of A is simply the solution space of AX equals 0. Okay, let me go to the whiteboard. Okay, so you have T sub A. So you have the map T sub A from Rn to Rm. Okay, it's left multiplication by A. And so if you have a vector x, which is in Rn, so here's your vector x in Rn. Okay, and so there's n components, x1, x2, dot, 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 x sub n. Okay, so you take that n tuple written as a matrix, a column matrix, and you left multiply it by the matrix A. So this is the matrix A, which is this is the matrix A, which is m by n. This matrix X, so it's A times X, and this is n by 1. Right, so the inner entries are the same, and the outer entries determine the size of the product of the matrices. So you get an m by 1 matrix. So the result of this is an m by 1 matrix. And so the output is, right, sitting in Rm. And so this Rm is made up of these outputs are in Rm. Okay, there's m components to these vectors. Just equal sign writing it down. Okay, so the input is these vectors in Rn, right? So your inputs are these vectors. You're left multiplying the A, and then the result is your output, which is in Rm. And you're saying an m by n matrix times n by 1 matrix, and the result is an m by 1 matrix determined by the outside, right? And the m and 1 tell you the size of the product of those two matrices. It's m by 1, right? M by 1. Okay, because the inner entries are the same. The inner ones, they have to be the same. Okay, so so now you have an m by 1 vector in the output. Okay, so the kernel of the kernel of this space are all the vectors x that you would plug in such that the output is 0. Well, AX equals 0. The solution space for this equation the solution space for AX equals 0, that's the null space of A. The null space of A is the solution space of AX equals 0. It's all the vectors x such that AX equals 0. And so equivalently, that's the kernel. Equivalently, that's the kernel of the map T sub A. Well, I want to write equivalent, but I guess the way I'm writing it, I wouldn't write equivalent. Kernel of T sub A is equal to the solution space or the null space of A. Is equal to null space of A. The kernel of T sub A is just all the vectors x that when you plug into the map T sub A, the output is 0. Or in other words, all the vectors x such that AX is equal to 0. Because AX is the map T sub A of x. T sub A of x is AX. And so that means the kernel of T sub A is all the things that would be mapped to 0. And so by the map T sub A. So all the things that would be mapped to 0 by T sub A would be all the vectors x such that AX equals 0. So the kernel of T sub A is equal to null space of A. So that's what I said in Word. Okay, so the kernel of T sub A is the null space of A. And the range of T sub A is the column space of A. So the range of T sub A, the range of T sub A is the column space of A. So if A, I'm still talking about this, but I just need more space. So I'm going to just continue it here. So if you have the matrix A, and you have an n by 1 vector x here, made up of components x1, x2, to xn. Then if you left multiply it by A, you want to look at the column space of A. So the columns of A are made up of a first column, a second column, a third column, dot, dot, dot. So A is an m by n matrix. So there are m rows and n columns. So that means there are n columns. So we'd stop at Cn. Okay. And so you can express this product as equaling to x1, C1 plus x2, C2 plus dot, dot, dot plus xn, Cn. Now the x's, these terms are just numbers. So this is a linear combination of the columns of A. And so what this is saying is that AX is equal to a set of all linear combinations of the columns of A. So as X ranges over all possible vectors X, then what you're getting is that all the values of AX are all the linear combinations of the columns of A. Okay, so this is a linear combination. Right, of the columns of A. Okay, so this is a linear combination of the columns of A. And so the range of, see specifically what I'm saying the range of T sub A is the column space of A. So the range of T sub A, denoted as R of T sub A, the range of T sub A is equal to the column space of A because, let me just, okay, so the range of T sub A, because AX is equal to T sub A of X. T sub A of X is the image under T sub A of X. It's left multiplication by A. So if T sub A is left multiplication by A, then T sub A of X is AX. So T sub A of X can be thought of also a linear combination of columns of A. Okay, so the range of T sub A are all the linear combinations of the columns of A. But the set of all linear combinations of the columns of A is the column space of A. The column space of A is the span of the columns of A. The span of a set is the set of all linear combinations of that set. So the span of the columns of A is the set of all linear combinations of the columns of A. And T sub A of X, every image, T sub A of any vector X is a linear combination of the columns of A. And so if you consider all the T sub A of X's, that corresponds with all the linear combinations of the columns of A, which is the span of the columns of A, which is the column space of A. So the range of T sub A and the column space of A are both the set of all linear combinations of the columns of A. And so they're equal to each other. Okay. Okay. Theorem 8.13. If T from V to W is a linear transformation, then the kernel of T is the subspace of B, and B, the range of T is the subspace of B. Okay, of W. Okay, so I showed that they are I showed that they're contained in them, but this theorem goes further and says that they are subspaces. Okay. Okay, let's keep going. Okay, so next is a definition. Okay, so let T from V W be a linear transformation. If the range of T is finite dimensional, then its domain, its dimension, is called the rank of T. If the kernel of T is finite dimensional, then its then its dimension, it's called the nullity of T. The rank of T is denoted by rank T, and the nullity of T is denoted by nullity of T. Okay, so let me say this again. So you have a linear transformation T from V to W. If the range of T is finite dimensional, so the range of T is a subspace of W, right? W is a vector space. The range of T is a subspace of W by this theorem, 8.13. A subspace of a vector space is a vector space. So the range of T is proven to be a vector space. A vector space has a basis, right? And so if that basis has if every basis, which has the same number of vectors in it, if every basis of the range of T, which is a vector space, has a finite number of vectors in it, it's finite dimensional. So if the range of T is finite dimensional as a vector space, then its dimension is called the rank of T. And if the kernel of T is finite dimensional, then its dimension is called the nullity of T. In this theorem, it also concludes that the kernel of T is a subspace of V. V is a vector space. And so saying that the kernel of T is a subspace of the vector space V is saying that the kernel of T is itself a vector space, right? A subspace of a vector space is a vector space. So the kernel of T by part A is also a vector space with its own bases. And so take any of those bases, any basis, and count the number of vectors in it. If there's finitely many, that tells you the kernel of T is finite dimensional. Okay, the dimension of a vector space is telling you its size. Okay. Okay, so the rank of T is denoted by rank of T, and the nullity of T is denoted by nullity of T. Okay, theorem 8.1.4. If T from V W is a linear transformation from a finite dimensional vector space V to a vector space W, then the range of T is finite dimensional. And the rank of T plus the nullity of T is equal to the dimension of the vector space V. And this is equation 7 of this section. So if T from V to W is a linear transformation from a finite dimensional vector space V to a vector space W. And so here W could be finite or infinite dimension. It's not said, right? So it could be either. Then the range of T is finite dimensional anyway. And you have this equation. Okay. So just knowing that the domain is finite dimensional, that means that the range has to be finite dimensional, even if W is infinite dimensional. Okay. Note, if T sub A from Rn to Rm, where here A is M by N, is an M by M matrix, is multiplication by A, the kernel of the map T sub A is the null space of A, and the range of T sub A is the column space of T sub A, which I mentioned earlier. Okay. Thus, by the theorem above, by theorem 8.1.4, we have that rank of T sub A plus the nullity of T sub A is equal to N. Okay, so here we're just replacing the rank of T by the rank of T sub A and the nullity of T by the nullity of T sub A. And here, instead of the dimension of B, which is the dimension of the domain, we're thinking about the dimension of Rn, the domain of T sub A. The dimension of Rn is n. So where here we have V, an arbitrary vector space, and here's the dimension of that vector space. Here, we specifically have n space as the domain. And so if n space is this domain vector space, the dimension of it is n. So we're just looking specifically, more specifically in this note in this theorem. Okay. Okay. That's the end of 8.1, and next is 8.2. 8.2 is on compositions and inverse transformations. Okay, so this is definition 1. If T is from B to W is a linear transformation from a vector space B to a vector space W, then T is 1-to-1 if T maps distinct vectors in capital B into distinct vectors in W. Okay, so this is a definition of T being 1-to-1 as a linear transformation. Okay, so it's just like the definition of 1-to-1 for a regular function. If T from B to W is a linear transformation from vector space B to vector space W, then T is 1-to-1 if T maps distinct vectors in B into distinct vectors in W. That means that it never is the case that two different vectors in B are mapped to the same vector in W. Okay, so what this definition says is that for a 1-to-1, that's short for 1-to-1, is that for a 1-to-1 linear transformation, T would never map two different vectors to the same one. Okay, so whenever you have two different vectors, T would have to map it to two distinct vectors. Definition 2. Definition 2. If T from B to W is a linear transformation from vector space B to vector space W, then T is onto if every vector in W is the image under capital T of some vector in B. Of some, you can write some or at least one. I'm going to write at least one. Okay. So if T from B to W is a linear transformation from vector space B to a vector space W, then T is onto if every vector in W is the image under T of at least one vector in B, right? So when you have a linear transformation B to W, W is not necessarily the range of T. T doesn't necessarily map something to anything in W. There could be vectors in W that are not mapped to by anything in B under T. But there are such linear transformations where that does happen. That's called an onto linear transformation. A linear transformation is onto when every vector in W is mapped to by something in B by T. Okay, so for every vector in W, there's some vector in capital V that T would map it to that vector in W. That's an onto linear transformation. Okay, theorem 8.2.1. So we have the definition of a 1-to-1 linear transformation and a definition of an onto linear transformation. So T from V to W is a linear transformation. V and W are vector space. Then the following statements are equivalent, which means they have the same, which means that the following statements. Have the same truth value. Okay. So A, T is 1 to 1. That's for sure. B, the kernel of T is equal to the 0 set. Those two statements are equivalent. They have the same truth value. So this theorem is not saying that either statement is true or false. It's just saying that both of their truth values are the same. So when one is true, the other is true. When one is false, the other is false. So if you can prove either one of these to be true or false, then you know the other one is the same in truth value. Okay, this is if T is a linear transformation. And these two statements have the same truth value. Theorem 8.2.2. If V and W are finite dimensional vector spaces with same dimension, and if T from B to W and if T from B to W is a linear transformation, then the following statements are following are equivalent. This means the following are equivalent, right? I've used it before. So then the following are equivalent, same in truth value. A, T is 1 to 1. B, the kernel of T is equal to the 0 set. And C, T is onto. Okay, I guess I'll put all lowercase onto. T is onto, and meaning that, I'm just reminding the definition of onto, meaning that the range of T is equal to W. It's codomain. Okay, so if V and W are finite dimensional vector spaces with the same dimension, and if T from V to W is linear transformation, then instead of having two equivalent statements, we have three. So if we know a little bit more, if we don't just know that's linear transformation, we also know that V and W are both finite dimensional and the same dimension. We know a little bit more. If a little bit more things happen, then we can add a third statement to this equivalence. Okay, examples. Example 1. If T sub A is from Rn to Rm is multiplication by an M by N matrix A, right? We're always assuming left multiplication unless said otherwise, right? So if it just says multiplication by matrix A, it means left multiplication by default, okay? So if T sub A is multiplication or left multiplication by an M by N matrix A, then T sub A is not 1 to 1 if M is less than N and is not onto, capitalize not, and is not onto if N is less than M. Okay, so if M is less than N, then that would mean that the dimension of the domain is larger than the dimension of the codomain. That means that the domain is larger than the codomain. That means you have more vectors here than here. And so that means that there's more vectors in the domain than codomain. And that would mean that two different vectors here would have to map to some same vector in Rm. Distinct vectors cannot always be mapped to distinct vectors because we do not have as many vectors in the codomain as we do in the domain. So T sub A cannot be 1 to 1. if the codomain is smaller than the domain, or if m is less than n. But by smaller, I mean Rm and Rn, right? Okay, so n is but smaller, okay. And is not onto if n is less than m. So if your domain space is smaller than your codomain space, it cannot be onto. Because even if every distinct vector in Rn is mapped to a distinct vector in Rm, the most number of images you could have is Rn. And so if Rm is even bigger, then that means you could not possibly get to every vector in Rm. So if n is less than m, if the domain is smaller than the codomain, then your function is not onto. Okay? So once m does not equal n, then it cannot be both one-to-one and onto. Okay? So when n equals m, from theorem much earlier, 4.10.2, T sub a is both one-to-one and onto if and only if a is invertible. Okay? So from theorem 4.10.2, T sub a is both one-to-one and onto if and only if a is invertible. Okay, so example 2. So when n equals m, that happens. Okay? If n does not equal m, then it cannot be both one-to-one and onto because it would fail one of these things. Either m would be less than n or n would be less than m, meaning it would either not be one-to-one or not be onto. Okay, example 2. We have T1, which is a map from P3 to R4. Remember, P3 is the vector space of polynomials of degree at most 3. So you could have degree 2 polynomials in here. It's just the space of all polynomials of degree at most 3 under standard addition of polynomials and standard scalar multiplication of polynomials. That's a vector space P3. It's a set of polynomials of degree at most 3, along with the operation of standard addition and the operation of standard scalar multiplication of polynomials. Those 3 things are a team called vector space, which is abbreviated by P3. So T1 is from P3 to R4. R4 is 4 space, the vector space of all 4 tuples, standard addition and standard scalar multiplication. R4 is shorthand for that vector space. But you were thinking of images as being vectors in R4. So T1 is from P3 to R4. And T sub 2 is from M sub 2 to R4. And it's defined by T1 of A plus BX plus C x squared plus dx cubed. That's T1 of a third degree of a polynomial of a degree at most 3. It's at most 3 because d could equal 0, which would mean that it would have be degree at most 2, and then c could also be 0 and b could be 0. You could have this as a representation of a constant. So this is a degree. This is the representation of a degree at most degree 3. But this is the representation, general representation of a polynomial of degree at most 3, which is a general representation of any polynomial P3, which is all the ones of degree at most 3, but not just 3. Okay, so T1 of that is equal to now A, B, C, D. Okay, so what we're doing is we're mapping. Okay, so that we're defining our map T1 as being that, and T2 we're defining as being, well, if you input into T2 a 2x2 matrix, which is an element of M sub 2, the vector space of 2x2 matrices, and the entries are A, B, C, and D, and T2 of an arbitrary 2x2 matrix would still be the 4 tuple A, B, C, D. Okay, so let's bring this here. So we have T1 and T2 both defined as by that. So these are both one-to-one and onto. And so as proved by showing their kernels contain only the 0 vector. Okay, So the kernel of each map is a set of all vectors that are mapped to 0. So note that the only vector in P3 that T1 maps to 0 in R4, which is 0, 0, 0, 0. That's the 0 in R4. So the only vector in P3 that T1 would map to that is the polynomial where A, B, C, and D are 0. So that would be is the 0 polynomial in P3. And so the kernel of T1 is only the 0 set. The only thing that T1 would map to 0 is the vector 0 in P3. And then so we have that. So what we have is that, so they're the same dimension. P3 and R4 are the same dimension because the space of all polynomials of degree at most 3 is dimension 4 because you have a constant term here. You have A plus BX plus CX squared plus DX cubed, right? See the coefficients A, B, C, D. So it's 4-dimensional and R4 is 4-dimensional. P3 and R4 are the same dimension, same finite dimension. And this is a linear combination. So because we have a linear combination from one vector space V to one vector space W, where they're both finite dimensional in the same dimension, Theorem 8.2.2 says that because we show the kernel of it was 0, that means that it's both 1-to-1 and onto. So T1 is both 1-to-1 and onto. Okay. So by using theorem, by applying theorem 8.2.2. Okay. And so that shows the kernel of T1 is 0. And so very similarly, you can show T2 is also 1-to-1 and onto. Okay. So also by similar reasoning, the kernel of T sub 2 is also the 0 set. And so by theorem 8.2.2, T sub 2 is both 1-to-1 and onto. Okay. And so that shows that both T1 and T2 defined in this way are both 1-to-1 and onto. Okay. Definition 3. If T1 is from U to V, and T2 is from B W, are linear transformations. They both satisfy the two properties for linear transformation. Then the composition of T2 with T1 denoted by T2 circle T1 is the function defined by T2 circle T1 of U. Input vector is little u because the domain is capital U here. So this is equal to T2 of T1 of U. And so you read it from left to right, but it's actually acting from right to left. So T2 composed of T1 means first T1, then T2. So you read from left to right, but the composition is really from right to left. Okay, so whatever one is it goes from the order of the applying the function goes from right to left. So first T1 and then T2 of that. And so this is equation 1 in this section. And this is where little u is a vector in capital U. And lowercase letters are usually used to denote vectors, and capital case are usually used to denote vector spaces. Okay, so let me just draw a picture of this composition on the whiteboard. So, okay, so you have this first domain, you have a second domain, you have a third domain. This is U, this is V, and this is W. So if you have a vector U in vector space capital U, you could talk about T1 of U, which is the image under T1 of U. So T1 would map this to this. So that would be T1. And then T2 would map T1 of U to this point here. So this would be the map T2 from V to W. And the image under T2 of T1 of U would be T2 of T1 of U. That's T. Okay, so it's T2 of T1 of U. So T1 of U, so T1 maps U to T1 of U. T2 maps T1 of U to T2 of T1 of U. Now, if you take the map T2 composed with T1, T2 composed with T1 would be the map that would send U, and U to T2 of T1 of U in W, in capital W. See that? So T2 composed with T1 is a composition of T1 and T2. Of T2 with T1. T1 first, then T2. Okay, so that's a picture of a composition of linear transformations. Okay, this is theorem 8.2.3. If T1 is from U to V, and T2 is from V to W, so if those are linear transformations, then the composition of T2 with T1, or T2 composed with T1, is a map from U to W, and it is also a linear transformation. So a composition of linear transformations is itself a linear transformation. Okay, example 7. If T, the map T from B to itself is a linear operator. So it's a linear transformation, but the domain and codomain are both B the same. And if I from B to itself is the identity operator. So it's an operator because it maps V to itself, and it's the identity one because it maps everything to the identity. I mean, then it maps every vector to itself. Then for all vectors, little v and capital V, we have that composition of T with I of vector little v is equal to T of I v. But the I of v is equal to itself v because the I is the identity operator. So I of v is v because I is the identity operator. The identity operator maps a vector to itself. So I of v is going to be v. I is going to map v to itself. So T composed with I of v is T of I of v. I of v is v, so that equals T of I of v is equal to v. So what we're saying is T composed with I of v is T of v. Okay, now if you go in the opposite direction, I composed with T of v will then be I of T of v. But now this is still the identity operator. And so it maps vectors to themselves. So now V is a vector, but T of V is also a vector. So I would map T of V to itself. So I of T of V would equal T of V. Okay, so T composed with I of V is equal to T of V, and I composed with T of V is equal to T of V. And so what this implies that T composed with I is equal to T, and I composed with T is equal to T. This is equation 2 in this section. So saying the composition map T composed with I, right, is the same as T, because you're saying the image under T composed with I of V is equal to the image under T of V. So T composed with I is doing the same thing as T to any vector V. So that means the map T composed with I is equal to T. I composed with T is doing the same thing for any vector V as T does to that same vector V. So I composed with V is equal to T. I composed with T is equal to T. So these two lines here give you these two equations. Okay. So let T1 be the map from U to V, and T2 be the map from V to W, and T3 be the map from W, Y. Let them be linear transformation. Then if you take T3 composed with T2 composed with T1, this is equal to T3 composed with T2 composed with T1 of U, which is equal to T3 of T2 of T1 of T1 of U. Okay, so the map T3 composed with T2 composed with T1 works just like T2 composed with T1. You're going from right to left. So this means first T1 applied to U, then T2 complied with that, and then T3 applied to that. Okay, so you're reading from right to left into out. And so this is explaining the composition of 3 linear transformations, where before it was only 2. Okay, the 3 is just, I'm not multiplying by 3, it's just noting the equation. Okay, so then if T from V to W is a 1-to-1 linear transformation with range R of T, and if W is any vector in the range of T, R of T, and the inverse of T denoted by T -1 sign there, T inverse, denoted by that symbol, defined on the range of T, maps W back into V, where T of V is equal to W. Okay, and so for this is on the whiteboard. Okay. 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 Okay, so let me draw a picture of that. So if T from V to W is a 1-to-1 linear transformation with range R of T, if W is any vector in the range of T, then the inverse of T, denoted by T inverse, defined on R of T, the range of T, maps W back into V, where T of V equals W. Okay, let me draw a picture of this. very often easier to see something with a picture than it is in words. So picture says 1,000 words. So T from V to W is 1. That's denoted by T inverse. Okay. So maybe I'll write that in. So denoted by T inverse. Okay, the superscript -1 there. Okay, so what's happening here is that if you have your domain space V, and if you have your codomain space, well, so then you have the range of T. Okay, so you have V, and you have the range of T. And so if you take a vector little v in the vector space V, T would map it to something in the range of T, right? The range of T is made up of all the images under T of vectors little v and capital. Okay, so T would map little v to a point in R of T. Call that point W. So W is equal to T of V. Okay, so W is now a point in the range of T, which means that it's mapped to by something in capital V. So we are allowed to talk about this point. So W is equal to T of V. So now T inverse, we're defining the map T inverse here. T inverse is a map that will, T inverse, it's denoted like this. T inverse is the map that would take a point W in the range of T and map it to the point in V, vector space V, that T mapped to that point W. So while T would map V to W, T inverse would map W to V. Okay? But keep in mind there's a requirement. T is a linear transformation, but it's also one-to-one. It's not the only requirement, but it's something important. One of the requirements is that you have a one-to-one map T. T cannot map two distinct vectors to the same vector. Why not? Because if it did, right, if you had a domain and you had a range, if you had V and RV and RT, but you had a T that was not one-to-one. So if T is not one-to-one, that's not the case here, right? T is one-to-one, but if it was not one-to-one, then what would happen is you would take two different distinct vectors in V, and they would map to the same vector in R of T under capital T. And then if that happened, right, if you had a V1 here and a V2 here, and T mapped V1 to a point W, and it mapped a vector V2 different than V1 to the same vector W, if I wanted to define a map that would send a point in the range of T back to the point that T mapped to it in V, there would be a problem, right? Because now there would be no one choice. I'd have two different options, but it would not define a map. It would not define a function, right? If I wanted to say, well, what I want to do is I want to choose a vector V. I want a vector V where T of V is equal to W. There are two vectors in this case, at least two. And so I do not have a well-defined function, right? I cannot say that the T inverse of that W is equal to the V that T maps to W, because there are more than one of them, right? This is not a well-defined map under this situation. But if T is one-to-one, there is only one vector that T would map to W, this little v. And so I can have a well-defined map T inverse from W to V. There's nowhere else it can go, because in the requirements is that T is one-to-one. Okay. Okay. So the picture's on whiteboard. Okay, so here in this situation, T inverse from the range of T into the vector space V is a linear transformation. And T inverse of T of V is equal to V. and T T inverse of V is equal to V. Sorry, it's equal to T of T inverse of W is equal to W. Okay, so this is equation 5 in this section. The one above it is equation 4 section. Okay, so T is a map whose domain is V, right? T is a map whose domain is capital V, and so the vectors you would plug into T are little v. T inverse is a map whose domain is capital W, and so the vectors you would plug into are little w. And so T and T inverse cancel each other out. Like additions, like 1 plus minus 1 would cancel each other out. T inverse composed with T would cancel each other out. And the vector you started with would be the same as the vector you ended with. So T and T inverse cancel each other out. 1 plus minus 1 is 0. Minus 1 plus 1 is 0. T inverse composed with T is the identity. T composed with T inverse is the identity. It's kind of like that. They're opposites. Okay, and so opposites cancel each other out. So if T1 from U to V and T2 is from V to W are one-to-one linear transformations, then A, T2 composed with T1 is one-to-one, and B, T2 composed with T1 inverse is equal to T1 inverse composed with T2 inverse. Okay, this says that the inverse of a composition of one-to-one linear transformations is the composition of their inverses in reverse order. Okay, so T2 composed of T1 inverse is just the composition of their inverses in reverse order. Okay, and so if you have T3 composed with T2 composed with T1 inverse, this is equal to T1 inverse composed with T2 inverse composed with T3 composed with T3 inverse. It's just the same idea. The composition of the inverse of a composition of these functions is the composition of their inverses in reverse order. And then if you have T sub CBA inverse, that means it's the inverse here. If it's the inverse of left multiplication by CBA, then it's equal to left multiplication by A inverse, left multiplication by B inverse, left multiplication by C inverse. So that means first left multiplication by C inverse, then B inverse, then A inverse. This is equation 9 in this section. So if you have T sub CBA, which is equal to of a vector x, right? Then what that would be is CBA of x. You're left multiplying by CBA. The inverse of that map, the inverse of the CBA map, if you plug in x into that inverse, then so the inverse would be right. So if you have a CBA, you have vector x, what you want to do is the inverse would get it back to x. So what you'd have to do is you'd have to left multiply it by C inverse. You have to multiply it by B inverse, left multiplied by A inverse. Then the C's would cancel. After the C's cancel, then the B's would cancel and the A's would cancel, and you get back X. So the inverse of CBA, left multiplication by CBA, is equal to left multiplication by A inverse, B inverse, C inverse. Okay, so the inverse of left multiplication by CBA is left multiplication by A inverse, B inverse, C inverse. And left multiplication by A inverse, B inverse, C inverse is first left multiplication by C inverse, then left multiplication by B inverse, then left multiplication by A inverse. And that's why the inverse of T sub CBA is equal to T sub A inverse times T sub B inverse times T sub B inverse. That's how I get that. That's how you get that. Okay, so the next is 8.3, which is on isomorphisms. This is definition 1. A linear transformation T from V to W that is both one-to-one and onto is an isomorphism. And W is said to be isomorphic to V. So this is the definition first of an isomorphism. If you have a linear transformation T from V to W that is both one-to-one and onto, that's what then is called an isomorphism. If you have an isomorphism from vector space V to vector space W, then you say that W, the vector space W, is isomorphic to V. There exists an isomorphism T from V to W. Okay, so T from V to W is an isomorphism. Implies that T inverse, which is a map from W to V, it goes in the opposite direction. So from W to V is also an isomorphism. Okay, so we say that V and W are isomorphic, and that T is an isomorphism between V and W. Once you find that T is isomorphic, once you find that W is isomorphic to V, you could show that V is isomorphic to W. Once you have an isomorphism from V to W, you can also get an isomorphism from W to V. So instead of specifying a direction, you just don't, because one direction implies the other. So you would not say that W is isomorphic to V. You would say that V and W are isomorphic. And you would not say you have an isomorphism from V to W. You would just say that you have an isomorphism. There is an isomorphism between V and W. And so when you talk about it, you get rid of the direction. Either direction implies the other. Okay. Next is theorem 8.3.1. Every real n-dimensional vector space is isomorphic to Rn. Okay, so I am saying 2 here, but by saying 2, I don't mean that I'm saying 2 just because I want to talk about something about one of the spaces, right? So you do say 2, but in a different way, right? I want to show that real n-dimensional vector spaces are isomorphic to some other space, in this case Rn. So I would say 2 there. You would say 2 there. The between is referring to just the idea that you always don't just know one, you know the other. But here you're saying you're given n-dimensional vector spaces, and you can say that they're isomorphic to this space Rn. Okay, so that's why 2 is there. Okay. Theorem 8.3.2. If S is equal to this set, V1, V2, V sub n is a basis for a vector space capital V, then the coordinate map that maps U to the coordinates of U relative to that basis S. You can call the map T capital T. This is an isomorphism between V and R n. Okay, so what's happening here? Theorem 8.3.2 says if S is a basis for vector space V, and the indices are going from 1 to n, which means that it's a basis with n vectors, saying that this vector space V is n-dimensional, finite dimensional of dimension n. So if S is a basis for vector space V, telling you something right there, then the coordinate map, which maps each vector little u in V to its coordinates relative to this basis S, then that map is an isomorphism between V and Rn. Okay, so what it's doing is it's taking every vector u in V and it's finding its coordinates. And so it's mapping every vector to its coordinates relative to this basis S. The coordinates of a vector in a vector space relative to a basis are the coefficients used to represent that vector as a linear combination of the basis vectors in the basis. Okay, so meaning of this. Okay, so given a basis capital S here, right? Given a basis capital S for the vector space S, given the basis capital S, we can express any vector u in capital V as u is equal to C1 V1 plus C2 V2 plus dot 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 plus Cn plus Cn Vn. And not only can you express any vector u, you can express any vector u uniquely in V as any vector in V uniquely as this. Uniquely, there's only one way. So that means there's only one way to get these numbers C1 to Cn, these coefficients C1 to Cn, right? And so there's only one way to do that. And so there is exactly one coordinate of u relative to the basis S. There's exactly one coordinate of u, exactly one assignment of exactly one coordinates of u. There's exactly one n tuple for the coordinates of u relative to the basis S, namely the coordinates of u relative to this fixed basis S is equal to that n tuple, right? C1, comma C2, comma dot dot dot, comma Cn. Right, those are the coefficients there. Since there's only one way to do this, exactly one way to do this, there's exactly one n tuple C1 to Cn in which this happens. And those are the coordinates of that vector u relative to this basis S. When you change the vectors in this basis, you would change the constants possibly that would express u as a linear combination of those vectors. So changing the basis is changing the coordinates of u relative to that basis, right? If you have a, let's say, if you had an axis here and an axis here, and you had a point here, then if you thought of each axis as kind of one of those basis vectors, you would travel a certain distance along one axis and then another distance along the other, and then that would be how you get to that pink point. If you change your axes, if you change your basis vectors, but you think of the exact same point, to get to that point, you'd have to go possibly a different distance along each of those coordinate axes to get to the same point. And so then you would go to the same point in a different way. Okay, the basis vectors in a way is the the rule in which you get to each point are like the axes in your space, which you would travel along to get to any point. If you change the axes, you change the ways you would get to all the points in your space. You would change the coordinates of that point relative to that basis. So let's say this was like 3 and this was line 2, then the coordinates of this point relative to that basis would be 3, 2. It would be 3 times one base vector plus 2 times the other. Let's say this one was 4 and this one was 1. Then that would be saying that the same point would be 4 times one of the base vectors plus 1 times the other. And so the coordinates of every point in vector space are the coefficients of the linear combination that used to express that vector with those base vectors. Okay, so the easiest way to visualize it is with the axes in that picture. Okay, so example 1 of this. So if you have a0 plus a1x plus dot 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 plus a sub n minus 1 x to the n minus 1. If you have a map T, that would map that to the n tuple a0, comma a1, comma dot dot dot, comma a sub n minus 1. It's an n tuple because even though you end with a sub n minus 1, you start with 0. If you have a list that starts at 0 and ends at n minus 1, there's actually n things in the list, even though it ends at n minus 1. So this is an n tuple, starting from a0 to an minus 1. So that what this map T does, this defines a map T. Okay, so this defines the natural isomorphism between Pn minus 1 and Rn. Okay, it's Rn because, like I said, this is an n tuple. Right? It's not about the indice. It's about the fact that there are n components of this thing. There are n components, right? The first component is a0, the second component is a1, the nth component is a sub n minus 1. This is an n tuple, an object in Rn. And this is a polynomial of degree at most n minus 1, which is an object in Pn minus 1. With this map that sends this polynomial to that n tuple is a natural isomorphism between Pn minus 1 and Rn. It's a linear transformation that is both one-to-one and onto. It is a linear transformation that is both one-to-one and onto. Okay, that's the definition of a linear transformation. Example 2. Okay, if you have a transformation that sends a 2x2 matrix whose entries are A, B, C, D, and it maps it to the 4 tuple A, B, C, D, then this defines an isomorphism between M sub 2 and R4. Okay, it takes matrices in M sub 2, takes matrices in the vector space of 2x2 matrices and maps them to 4 tuples in R4, where it's just the entries of that matrix. So the matrix ABCD gets mapped to the 4 tuple ABCD. That defines a natural isomorphism between M sub 2 and R4. It's a one-to-one onto linear transformation. Okay, so that's the end of material. I want to go over a certain problem. So, 1 second. Okay, so in 8.3, there's one problem I always go over at the end here for this section. So I'm going to do that again here now. So in 8.3, we'll look at number 12. Okay, so this is 8.3, number 12. Okay, so for 8.3, number 12, let's look at the so let's look at this one, 8.3, number 12. So this is, I have this online already on Blackboard. So if you go to Blackboard, you're on the home page, and you go, it's right here, I added this now. It's chapter 8, homework solutions. So when you do this homework, this is the file, you click that, and these are the solutions. And you click this, and this is a video of me going over the solution. Okay, so since this last homework is on the last day of class, I'm going over it both by giving the file, the solutions, and by giving you a video where I go over those solutions. Okay, so let me go back. Okay, so this is the one I want to go over. So this is the last one here. So the problem says, determine whether the matrix transformation T sub A from R3 to R3 is an isomorphism. The question is T sub A an isomorphism? Is it an isomorphism? Okay, where A is given as this matrix. So that's A. A is the left side of the partition of this matrix. It's the 3 by 3 matrix, 1, -1, 0, 0, 0, 2, -1, 1, 0. So the matrix transformation, left multiplication for that matrix A, is it an isomorphism? So what I did was I took a partition matrix. So the left side is A and the right side is the 0 matrix, 3 by 1, 0 matrix. I got that to reduced row echelon form. So when you get this matrix to reduced row echelon form, you get this augmented matrix. Now, if you look at this augmented matrix, this is a representation of the linear system where you have a matrix times x equals 0. The null space of this vector space has non-zero dimension. Its solution space has dimension 1 because it has you have two leading ones here, but there are 3 columns. So you have 2 leading variables and 1 free variable. And so the null space is non-zero. So the kernel of T sub A is not the 0 set. Or the nullity of A, the dimension of the null space is not 0. And so by theorem 8.2.1, that implies that T sub A is not 1 to 1. So theorem 8.2.1. So theorem 8.2.1 says, it's on page 458 of the book, 458. It says, if T from V to W is a linear transformation, then the following are equivalent. T is 1 to 1, and the kernel of T is a 0 set. It's in class, it's in the notes. This what I showed is that the kernel of T sub A is not 0. And so that means that T is not 1 to 1. Okay? The map 1 to 1 and the kernel being 0 set are equivalent by a theorem in the conclusion. So showing that the kernel is not the 0 set implies that the map is not 1 to 1. Once T sub A is not to 1 to 1, it cannot be an isomorphism. An isomorphism is a linear transformation that is both 1 to 1 and onto. T sub A is not 1 to 1, so it is not an isomorphism, and that's the end of that problem. Okay. All the other solutions are here, and the solution of this one is also on the video. So all these solutions are on the video, and I go over it. So you should do this homework and then watch the video and make sure you understand all these things where I go over the solution. Okay. Does anyone need help with stuff for the final? I mean, not the final, the next exam. Okay. So review for the review for the exam. Okay. Anyone have questions about the second exam if you want to ask me? I mean, not the review for test 3. Review for test 3. Okay, test 3, the one on Thursday. Okay, so right. So let's look at the practice. So okay, so the practice test for test 3, we have these problems, right? For determine whether the matrix transformation is an isomorphism. This is just like the problem I just went over. So what you do is you take the partition matrix A, you take the partition of A with 0, you get it to reduced row echelon form, and you see whether or not the kernel of T sub A is the 0 set or isn't, right? Okay, so we could do that now. So this is your matrix. Okay, so 4, -3, 0. So I'm going to go to the whiteboard. Okay. Oops. Okay, so here's your matrix A. It's 4. 4, -3, 0, 2, -1, 2, 1, 5, 7, 0, 0, 0. So I want to get this to reduce echelon form. So I'm going to multiply the first row by 1/4, 1, -3/4, 0, 0. The second row, I'm going to, I guess, rewrite it. 2, -1, 2, 0, 1, 5, 7, 0. So I'm just getting this to reduce echelon form with this step. Okay, I'm going to keep the first row the same. The second row, I'm going to take -2 times the first row and add to the second one. So I get 0. I get 6/4 minus 1, which is 1/2. -2 plus that, I get 2 and 0. For the third row, I take -1 times the first row and add it to the third row. 3/4 plus 5 is 23/4. Okay, so you just do negative. So 3/4 plus 5 is 23/4. Good. And so then 7 and 0. Okay, so we keep going here. And so now we have a 1, -3/4, 0, 0. I'm going to multiply the second row by 2. So you get 0, 1, 4, 0. Now I want to cancel. I'm going to take -23/4 times this second row and add to the third row to get rid of this bottom term here. Okay, so -23/4. So then that would be -23 plus 7, which is -16. And then that's 0. Okay, and so if I multiply the third row by -1/16, I get 0, 0, 1, 0, 0, 1, 4, 0, 1, -3/4, 0, 0. Okay, so now I got to row echelon form. The fact that I got to row echelon form means I see something already. But so now I have that the kernel. This implies, so I have a leading one here, a leading one here, and a leading one here, and there are 3 rows. So I have as many leading ones as I can. So this implies that the kernel of T sub A is equal to the 0 set. Okay, if I went further and got this to reduce echelon form, I would just go in the opposite direction, right? And I would add -4 to the third to the second. I would eliminate everything above each leading one. I could see that already with this pink step, but we can go further. And then you would take -4 times the third row, add to the second. You would take 3/4 times the second, add to the first. You would get this. So here you're seeing that the only vector that would map this, the only solution is the 0 vector. So the kernel T sub A is the 0 set. So that implies by the theorem, that T sub A is 1-to-1. Okay, but further, we have in class that if the dimension of the domain and codomain are the same, then it implies both 1-to-1 and ontoness. It's 1-to-1 and onto, and that's because T sub A is a map that maps R3 to itself. The dimension of the domain and codomain are the same finite dimension 3. And so that implies that T sub A is an isomorphism. Okay, so that's how you do that problem. So T sub A is an isomorphism. So hopefully that makes sense. So wait, where are we here? Okay, here. So you should be able to see the practice test here. So 4 is that T sub A is 1-to-1, since it's 1-to-1 onto and a linear transformation. Right, so it's a matrix transformation. Every matrix transformation is a linear transformation also. So you have it's a linear transformation and that's 1-to-1 and onto. So that answer is number 4. Okay, for number 5, it says find the characteristic equation, eigenvalues, and bases for the eigenspaces of this matrix. So let's do that. Okay, so let's go to the whiteboard. Okay, I'm just having it's good if you have the problem in front of you, right? So here's our starting matrix. A is equal to 1, 2, 1, 0, 2, negative 1, 0, 0, 1. That's our matrix A. We want to find the characteristic equation. So we want a determinant of lambda I minus A is equal to 0. That's the characteristic equation. And so that is equivalent to the determinant of lambda I, which is this matrix, lambda 0, 0, 0, lambda 0, 0, 0, lambda. It's lambda times the identity matrix minus A, which is that matrix there. 1, 2, 1, 0, 2, negative 1, 0, 0, 1. You want to find the determinant of that, and it equals 0. Okay, determinant of that is equal to 0. And so that's if and only if. Now, what is the difference of those matrices? So you have a 3 by 3 matrix. You have lambda minus 1 here. You have a negative 2 here. You have a negative 2 here. You have a negative 1 there. You have a 0 here. You have a lambda minus 2 here. You have a 1 here. You have a 0, 0, lambda minus 1 there. This is a triangular matrix. So the determinant is equal to 0. The determinant of a triangular matrix is the product of the entries on its main diagonal. So the entries on the main diagonal are lambda minus 1, lambda minus 2, and lambda minus 1. So the determinant of that upper triangular matrix is the product of those main diagonal entries, which is lambda minus 1 times its squared, just reordering it, lambda minus 1 squared times lambda minus 2. That's the determinant, and it's equal to 0. So this is the characteristic equation of this matrix A. Okay, that's the characteristic equation of that matrix A. So that finds the character. Now we want to find the eigenvalues, but the eigenvalues are just all the values of lambda that satisfy that equation. So that's lambda equals 1 and lambda equals 2. So those are the two possible eigenvalues. And so we found all eigenvalues there also. So find the characteristic equation, check. Find the eigenvalues, check. And find bases for the eigenspaces of the matrix. Okay, so we want to find the eigenspaces also. So there's an eigenspace corresponding to each eigenvalue. So let's find the eigenspace corresponding to each eigenvalue. So first you have lambda equals 1, right? You have the eigenspace corresponding to lambda equals 1. So the eigenspace corresponding to lambda equals 1 are all the solutions of lambda I minus A times X is equal to 0. Okay, where here lambda is 1. Right, lambda is 1 here. So it's a solution to I minus A times X equals 0. I minus A in parentheses times X equals 0. All the vectors X to satisfy that matrix equation is the eigenspace corresponding to lambda equals 1, the eigenspace corresponding to lambda equals 1. Okay, so I minus A. So I minus A is just, here we found I minus A inside of this determinant symbol. So I minus A is that, except when we plug in 1 for lambda. So it'd be 1 minus 1 here, which is 0. Negative 2, negative 1, 0, 1 minus 2 is negative 1. 1, that's a 0. 0, 0, 1 minus 1 is 0. So that's that. And then an augmented matrix because the right side is equals 0. So we want to find out the solution space here. Well, so we can get this to reduce row echelon form at least. So the first row I'm going to multiply by negative 1/2. So this is 0, 1, 1/2. 0, 0, 0. And so now I'm going to add this new first row to the old second row. And so this can become a 0. 1/2 plus 1 is 3/2. 0, 0. Okay, and so then one more step, I'm going to add, I'm going to multiply the second row by 2/3. So it's 0, 1, 1/2, 0. 0, 0, 1, 0. And the third row is just all zeros. Okay, so now we have this matrix. So, and then I could take -1/2 times the second row into the first. So we have 0, 0, 0, 0. We have 0, 0, 1, 0, 0, 1, 0, 0. Okay, so what this is saying is that the leading ones correspond to the leading variables. So x2 and x3 are leading variables and x1 is a free variable. So if we let x1 equal to t, if we let x1 equal to t, then x2 is equal to, you can see x2 is equal to 0, and x3 is equal to 0. And so the solution vectors to this I minus a times x equals 0 are all the vectors x1, x2, x3 satisfying those three equations. So you have x1, x2, x3. This is equal to, well, x1 is of the form just t, x2 is 0, and x3 is 0. So it's all vectors of the form t comma 0 comma 0. This is equal to all multiples t of 1, 0, 0. So t times 1 comma 0 comma 0. Okay, so that's the eigenspace corresponding to lambda equals 1. It's the set of all vectors. It's the set of all vectors of the form t times 1, 0, 0, such that t is a real number. Okay, so you can plug in any real number for t you want, and then t times that column vector would give you all the possible eigenvectors in the eigenspace corresponding to lambda equals 1. So that's for lambda equals 1. And then there's an eigenspace corresponding to lambda equals 2, which I'm going to have to go to the next screen. So you have lambda equals, was it 2? Lambda equals 2. So you have an eigenspace corresponding to lambda equals 2. And so for that eigenspace, it's the solutions of lambda, which is 2, lambda I minus a times x is equal to 0. So on the left side, we have 2i minus a. We originally had this matrix inside the determinant, which was lambda I minus a. So you just plug in lambda equals 2 there. So in the main diagonal, you get 1, 0, 1. It's a partition, so the 0 is on the right side, with the 0 on the right side of the equation. And then here we have the numbers -2, -1, 1. Okay, so now you want to get this to reduce echelon form. So now so you have this second row here, 0, 0, 1. You add -1 times that to the bottom row, and that goes away. So the bottom row becomes all zeros. And if you add this row to the first row, you get 1, -2, 0, 0. So now this is the matrix in reduced echelon form. So now if you look at the leading ones, you have a leading one here and you have a leading one here. That means that x2 is a free variable. So now x2 is a free variable. So let x2 equal to t. And so then x2 is equal to t, x3 is equal to 0, and x1, by how we define it, is equal to 2 times t. Because this first equation here, right, this first equation here is saying x1 minus 2x2 equals 0. And we set x2 equal to the parameter t. This is telling you x1 is equal to 2t. Okay, so x1 is equal to 2t. So that means that the solutions in this eigenspace x1, x2, x3 is equal to the 3-tuple 2t, t, 0. This is the same. So the eigenspace is the set of all vectors t times 2, 1, 0, such that t is a real number. And so that's the eigenspace corresponding to lambda equals 2. Okay, and so that answers the question on that exam. So find the characteristic equation, the eigenvalues, and basis for the eigenspace of the matrix. And so that's also good. Okay. Okay, so let's look at maybe number 2. Let R3 have the Euclidean, so I'll stay a little longer if you want to stay. I'm going to post the video online so you can watch online. The R3 have the Euclidean inner product and use a Gram-Schmidt process to transform this basis, U1, U2, U3, into an orthonormal basis. Okay, so to transform into an orthonormal basis, we need an orthogonal set, and then we need to make every vector of length 1. So let's first make an orthogonal set. So go to the whiteboard. Okay, so we have the U1, U2, U3. U1 is equal to the vector 1, 2, 2. U2 is equal to the vector -1, 0, 2. And U3 is equal to the vector 0, 0, 1. Okay, so those are your vectors. So what we want to do is use a Gram-Schmidt process to make an orthogonal basis from them called V1, getting V1, V2, and V3. So step 1 is that V1 is the same as U1. So V1 is 1, 2, 2. Step 2 is that the second basis vector, new orthogonal basis, is going to be equal to U2 minus the inner product of U2 with V1 divided by the norm of V1 squared by the formula I gave you. So this is equal to U2, which is -1, 0, 2, minus the inner product of U2 with V1. So you multiply corresponding components and add the product. So you get -1 plus 0 plus 4, which is 3. This is 3 divided by the norm of V1 squared. The norm of V1 squared is equal to the sum of the squares of the components of V1, which is 1 squared plus 2 squared plus 2 squared. So then you get this minus 1/3, 3 over 9 is 1/3. So this is equal to, oh, sorry, and then this is equal sign. This is a B1 here. Okay, so then this is also, this is minus 1/3, but times the vector V1, which is 1, 2, 2. Okay, and so this is equal to -1, 0, 2, minus, this is 1/3 times that. So it's 1/3, 2/3, 2/3. And so this is equal to -1 minus 1/3 is -4/3. And 0 minus 2/3 is minus 2/3. And 2 minus 2/3 is 6/3 minus 2/3, which is 4/3. So V2 is that. And then V3 is going to be equal to U3 minus the inner product of U3 with V1 divided by the norm of V1 squared, V1, minus the inner product of U3 and V2 divided by the norm of V2 squared times V2. Okay. That's right. Okay, so then, okay, so U3 is equal to the vector 0, 0, 1. This is minus the inner product of U3 and V1 is equal to 2. Divide by the norm of V1 squared, which we found was 9, times V1, which is 1, 2, 2, minus the inner product of U3 and V2, where V2 is here. So it's the only third component, so it's 4/3. So it's minus 4/3 divided by the norm of V2 squared, which is the sum of the squares of the vector V2. That's -4/3 squared plus 2/3 squared plus 4/3 squared. So that's 32/9 plus 4/9, 36/9, which is 4. This 4. Okay, so the sum of the squares is 4. And this is V2, which is negative 4/3. Negative 4/3 comma negative 2/3 comma 4/3, and that's multiplied by negative 4/3 divided by 4, which is negative 1/3. Okay, so then this is equal to 0, 0, 1 minus, now that product, which you get is 2/9, 4/9, 4/9. Now it's minus, so this is minus 1/3 times that. So this is minus 1/3. So this is negative 4/9, comma negative 2/9, comma 4/9. That's when you do that subtraction. You have 0 minus 2/9 plus 4/9, which is 2/9, comma negative 0 minus 4/9 plus 2/9, which is minus 2/9. And 1 minus 4/9, which is 5/9. 5/9 minus 4/9 is 1/9. So you get 2/9, comma negative 2/9, comma 1/9. That's V3. So we have V1, V2, and V3. Okay, so V1 is this vector, V2 is this vector, and V3 is that vector. So now I have V1, V2, and V3. They form an orthogonal basis. But the question asks for an orthonormal basis, which means you want the norm of every vector to be 1. Changing the norm of each vector doesn't change whether or not they're orthogonal. So you can just divide each of them by its norm to get corresponding unit vectors, which form an orthonormal basis from that orthogonal. So we're going to find the vectors W1, W2, and W3 to be the unit vectors in the same direction as V1, V2, and V3 correspondingly. So W1 is going to be equal to V1 divided by its length. So V1 is 1, 2, 2, and we found that its length squared is 9, which means its length is 3. Okay, so that implies the length is 3. So this is 3. This is 1/3, comma 2/3, comma 2/3. Now W2 is equal to the vector V2. We're making a vector V2 as being, we're making a vector W2 as V2 divided by its length. So V2 is negative 4/3, comma negative 2/3, comma 4/3. So you want to divide it by its length. So we have 9. So we have 16, 32, 36 over 9, which is 4. That's the length squared. 4 is length squared, so 2 is its length. So divide by 2. This is equal to negative 2/3, comma negative 1/3, comma 2/3. That's also a unit vector. If you take the sum of the squares, you get 1 squared. Okay, so that's W2. And then W3 is equal to, we're going to define as V3 divided by its length. We're just making every vector, constructing a unit vector in the same direction as the vectors V1, V2, and V3. So you have 2/9, comma negative 2/9, comma 1/9. You want to divide it by the length of V3, which is the square root of the sum of the squares of the components. So 2/9 squared plus negative 2/9 squared plus 1/9 squared, and the square root of that. So you get 4, 8, 9 over 81, which is 1/9, and the square root is 1/3. So the length of that vector is 1/3. And so now, so you multiply them down by 3, so you get 2/3, negative 2/3, 1/3. Okay, and so that's also unit vector. So now this W1, W2, and W3 form an orthonormal basis. We converted the original basis into an orthonormal basis. Okay, and here I call them W1, W2, and W3, and on the answer solution sheet, I call them U1 prime, U2 prime, and U3 prime. And so it is the same as, I got exactly the same thing. Good. 2/3, negative 2/3, 1/3. 2/3, Negative 2/3, 1/3. Okay, I wasn't looking. Good, same. Okay, so okay, so we got so that's number 2. Okay, so we got 2, 4, and 5 here. Okay, so for number 3, find a matrix P that orthogonally diagonalizes A and determine P inverse AP. Okay, so okay, so okay, so what you want to do is you want to find, okay, so the procedure for orthogonally diagonalizing a matrix, n by n matrix, is step 1, find a basis for each eigenspace of A. So we start with this matrix A. And so, okay, so, no, whiteboard. Okay, so quickly, okay, so, so find a matrix P that orthogonalizes and find P inverse AP. So if you have a matrix A, which is the matrix 2, 1, 1, 2, you want to find an eigenspace, you want to find a basis for each eigenspace of A. So first find the characteristic equation, lambda I minus A is equal to 0. Okay, this is if and only if you have the determinant of lambda I, which is lambda 0, 0, lambda, minus A, which is 2, 1, 1, 2. And you take the determinant of that difference and equals 0. So this is the characteristic equation. This is if and only if. Now the determinant of lambda minus 2, negative 1, negative 1, lambda minus 2. Terms of that matrix equals 0. It's a 2 by 2 matrix, which means you can find its determinant, AD minus BC. This is lambda minus 2 times lambda minus 2, and then minus negative 1 times negative 1, which is 1. Minus 1 is equal to 0. And so that now we have that. Multiply lambda minus 2 by itself, you get lambda squared minus 4 lambda plus 4, and then minus 1 is equal to 0. So this is if and only if lambda squared minus 4 lambda plus 3 is equal to 0. So that's the characteristic equation. But you can factor out the left-hand side. This is lambda minus 3 times lambda plus minus 1 is equal to 0. And so that means the two solutions of this characteristic equation are lambda equals 3 and lambda equals 1. So those are the two eigenvalues corresponding to that matrix, given matrix 2 by 2 matrix A. So each of them has an eigenspace, lambda equals 3 and lambda equals 1. So for lambda equals 3, you have the eigenspace corresponding to lambda equals 3, which is the solution space of lambda, which is 3, lambda I minus A times X is equal to 0. So all vectors X that satisfy that equation is the eigenspace corresponding to lambda equals 3. So this matrix is this matrix inside the determinant where you plug in this matrix here. This is lambda I minus A. So now plug in 3 for lambda, you get lambda I minus A. So this is the matrix 1, negative 1, negative 1, 1. I plugged in lambda equals 3 there. And so now I'm expressing that matrix equation as an augmented matrix, the linear system. So I get this to reduce echelon form. So this is 1 minus 1, 0. Add the first row to the second row. The second row is gone. So now I only have one row. And so now the leading one here, there's only one leading one here. That means that the first variable, x1, is a leading variable. So we only have one free variable, which is x2. So I'm going to set x2 equal to t. And x1 is already equal to 0. So that means the solutions to this system is equal to 0, comma t. And so the eigenspace corresponding to lambda equals 3 is a set of all vectors t times 0, 1, such that t is real. Okay, so a basis for this eigenspace is the vector 1, 0. So that's the eigenspace corresponding to lambda equals 3. The eigenspace corresponding to lambda equals 1 is then the solution space to 1i minus a times x is equal to 0. That's a 1 there. And so now the matrix representing that is plugging in lambda equals 1 into that red matrix there, which is negative 1, negative 1, negative 1, -1. 0 is on the right side. This is the augmented matrix representing that system. These are separate parts, right? So there's a cutoff here. This is lambda equals 3. Okay, and so now get this to reduced echelon form. So the first row multiplied by -1. Then add the new first row to the second row, you get zeros. And so now we have a leading 1 here. So the first variable is a leading variable. The second one does not correspond to a leading variable, so it's a free variable as a parameter. So set x2 equal to t also. So now x1, reuse that notation. So x1 is equal to 0. So the point x1 comma x2, a solution x1 comma x2 is equal to 0 comma t. And so the eigenspace corresponding lambda equals 1 is the set of all vectors t times 0 comma 1, such that t is real. So a basis for the eigenspace corresponding to lambda equals 1 is 0, 1. And so now we have a basis for both. We have basis vectors for both eigenspace corresponding to lambda equals 3 and for lambda equals 1. So step 1, we found a basis for each. Step 2 is apply the Gram-Schmidt process to each of the bases to obtain orthonormal basis for each eigenspace. Okay, this is already an orthonormal basis. That forms an orthonormal basis already because there's only one vector in it and it's of unit length. So those each are orthonormal bases for each of those eigenspaces. Step 2 is done automatically. Step 3, form the matrix P, whose columns are the vectors constructed in step 2. So we could say, let's say we say lambda equals 1 first. So this is 0, 1, and the lambda equals 3 next, 1, 0.
Wait, Professor,
So this,
0, 1 for the lambda equals 3?
no, I just switched. I did lambda equals 1 first, which is 0, 1. But I could do 1, 0 first anyway.
No, I mean, like, I'm pretty sure it's supposed to be 0, 1 for lambda equals 3, isn't it?
No, it doesn't matter. You can choose either one. What? Oh no, you're saying I wrote.
Yeah, I mean for that part.
Oh, okay. I see what you mean. Wait, okay. So x1 is 0. Next, yeah. So it's 0, 1. Okay, I see what you mean. Yeah. Thank you. Okay, so that's 0, 1. Yeah, I agree. Okay, so then that's that. Oh, okay. So okay, wait. I mean, okay. So here, x2 is t, but x1 is negative t. So if you solve for x1, you get x1 is negative x2 or negative t. So x1 is negative t. X1 is negative t. So that means that this is actually negative 1, 1. Okay. So x1 is negative t, x2 is t. So this is a negative t here. Okay, so x1 is t, x1 is negative t, and x2 is t. Good. So you got t times negative 1, 1. And you, so, okay, so now, okay, so I have to go back now. Okay, so you have an orthonormal basis for the eigenspace corresponding lambda equals 3. The eigenspace for the basis for the eigenspace corresponding lambda equals 1, the eigenvector is not of length 1. So you have to normalize it. So when you normalize that vector, the length of that vector is the square root of 2, because negative 1 squared plus 1 squared, square root of that, is equal to the norm of the vector negative 1, 1. The norm of the vector negative 1, 1 is the square root of the sum of its squares, which is equal to the square root of 2. So you divide that by its length to get a unit vector in the same direction. And so an orthogonal base, an orthonormal basis for that would be generated by the set just dividing by root 2. So it's negative root 2, root 2. This is an orthonormal basis for the eigenspace corresponding to lambda equals 1. So now when you form, so this is the one, that's good. Okay, so that erase that. Okay, so you have those two green ones, and so those are going to form the columns of the matrix P that orthogonally diagonalizes the original matrix. So let's say the first column is negative root 2. Oh, you have to, wait, sorry, you have to divide by root 2. So this is negative So it's negative 1 over root 2. And this is 1 over root 2. Okay, so that means that the entries on the first column are those entries in that. So you get negative 1 over root 2, 1 over root 2. And then the other one is 0, 1. So that matrix P, that's the matrix that orthogonally diagonalizes A. And determine P inverse AP for your choice. Whenever you choose, when you choose a P determined by the order of the columns, right? So P inverse AP is equal to diagonal matrix D, where the entries on the main diagonal correspond with the columns you chose. So in the first column, I chose the basis vector for lambda equals 1. So that means that in the first column, the entry in the main diagonal is going to be 1. In the second column, I chose the basis vector in the eigenbasis for corresponding to the eigenspace corresponding to lambda equals 3. And so that means lambda equals 3 there. And so that is P inverse AP for the P that I chose. If I switch the order of the columns, then I would switch the 1 and the 3 in the main diagonal of P inverse AP. Okay, so your choice in columns determines the order of the eigenvalues on the main diagonal. Okay, and so now we also found P inverse AP. Okay, and we found P, and we found okay, and so that is the solution to that problem. This is number 3, but this is number 3 continued. No, that was the other problem. Okay, so now okay, so we did number 3. Okay. Okay, so number 1 is left. So let me see quickly this. Find the geometric and algebraic multiplicity of each eigenvalue of the matrix A and determine whether A is diagonalizable. Okay, then find the matrix P that diagonalizes A and find P inverse AP. Okay, so okay, so find the geometric and algebraic multiplicity of each eigenvalue of the matrix A. Okay, so we want to find the eigenvalue. So it's determinant of lambda I minus A is equal to 0. The determinant of lambda I minus A. So the matrix you get is lambda I, so lambda minus 2, 0, 0, 0, lambda minus 3, 2, 0, negative 1, lambda. That's the determinant of lambda I minus A, and so it equals 0. And so now, okay, so now you find the determinant of this matrix. So let's find the determinant, and so let's take the so you get lambda minus 2. If you take the cofactor expansion along the first row, the other two terms don't matter. So it's lambda minus 2 times the determinant of lambda minus 3, 2, minus 1, lambda. Right, that equals 0. So the determinant of that submatrix, lambda minus 3 times lambda minus 3 times lambda, because AD minus BC, minus negative 2, which is plus 2. That equals 0. And so you have lambda minus 3. And then you have lambda minus 3 times lambda. That's lambda squared minus 3 lambda plus 2. That equals 0. Oops, 0. So you have lambda minus 3 times lambda minus 2 times lambda minus 1. Okay, and so that means that the 3 values of lambda are lambda equals 1, 2, 3. Those are the 3 eigenvalues corresponding for that matrix. Okay, so now we found the eigenvalues. So it says find the geometric and algebraic multiplicity of each eigenvalue. So the algebraic multiplicities of lambda are just the number of times lambda minus lambda naught appears in the factorization of the characteristic polynomial. So look, so lambda equals 1 has algebraic multiplicity 1. Lambda equals 2 has algebraic multiplicity 1, and lambda equals 3 has algebraic multiplicity 1, because the exponents for each of them is 1. Okay, so the algebraic multiplicities are 1 for each. Okay, so the algebraic multiplicities of lambda equaling to 1, 2, and 3 are each 1. Okay, and so that's because the exponents, that's since, right, so that's since lambda minus lambda naught appears exactly once and as a factor in the characteristic polynomial for each of them. So lambda minus 3 appears exactly once, lambda minus 2 appears exactly once, and lambda minus 1 appears exactly once in factorization, which means lambda equals 1, 2, and 3 are have algebraic multiplicities each equal to 1. So you have to look at the characteristic factorization of the characteristic polynomial in order to determine the algebraic multiplicities of each eigenvalue. Okay. So we have the algebraic multiplicities there. The geometric multiplicities of each of those eigenvalues are the dimensions of the corresponding eigenspaces corresponding to each of those eigenvalues. So for lambda equals 1, you want to find the eigenspace corresponding to lambda equals 1, and its dimension is the geometric multiplicity of lambda equals 1. Okay, so it says find the geometric and algebraic multiplicity of each eigenvalue. Okay, so the for lambda equals 1, keep in mind that lambda I minus a is this matrix. So lambda I minus a times x is equal to 0. You plug in lambda equals 1, you get -1, 0, 0. You get 0, -2, 2, 0, -1, 1. And you have the zeros over here. So now we want to get this to reduce echelon form. Multiply the first row by 1. Now multiply the second row by -1/2. So you get 0, 1, -1, 0. Now add the new second row to the old third row. And so you get the zeros here. This is in reduced echelon form. Okay, the leading ones, these are the leading ones here. Is one free variable, that's x3, which is equal to t. x3 is equal to t. That means x2 is equal to t, and x1 is equal to 0. Okay, so the eigenspace has dimension 1 because it has one parameter. So the eigenspace is of dimension 1. So the geometric multiplicity of lambda equals 1 is 1. Okay, so the geometric multiplicity of lambda equals 1 is 1. Okay, that's because there's one parameter. Okay, and now for lambda equals 2, you plug in lambda equals 2 into lambda I minus a times x equals 0. So you plug in lambda equals 2 and you get 0, 0, 0, 0, -1, 2, 0, -1, 2. And so you get this to reduce echelon form. And so when you do that, you get 0, 1, -2, 0. That cancels with this. So reduced echelon form, we get this. Okay, this is a leading 1. The only free variable is, well, so there are 2 free variables, x1 next. Wait, lambda equals 2, -1, 2, -1. Lambda minus 2. Oh, okay. That should be lambda minus 2. Thank you. Okay. Do a lambda minus 2 there. Thank you. Okay, so then there we go. Okay, so now, okay, so I have to, okay, so forget this. Okay, so now luckily I didn't this won't be less work after I make these corrections. So you have lambda minus 2 squared times lambda minus 1 is equal to 0. That means the eigenvalues are lambda equals 1 and lambda equals 2. The algebraic multiplicity of lambda equals 2 is 2, and the algebraic multiplicity of lambda equals 1 is 1, because the powers here. This is power 2, and this is power 1. So the algebraic multiplicity of lambda equals 1 is 1, and the algebraic multiplicity of lambda equals 2 is 2. The geometric multiplicity of lambda equals 1 is 1. And here, because we have one leading variable, we have x1 is equal to its own parameter. It's a free variable. And x3 is also equal to its own parameter. So that means that the dimension of the eigenspace corresponding to lambda equals 2 is of dimension 2. So the geometric multiplicity of lambda equals 2 is 2. The geometric multiplicity of lambda equals 2 is 2. Okay, and so now we have that the geometric multiplicity is always equal to the algebraic multiplicity for each eigenvalue. So that means that this matrix is diagonalizable. Okay, so the matrix is diagonalizable because the geometric multiplicity equals the algebraic multiplicity for every eigenvalue. Okay, it cut off the other one. The matrix is diagonalizable because the geometric multiplicity equals the algebraic multiplicity for every eigenvalue of the matrix. Okay. The geometric multiplicity is always at most the algebraic one, but when they're always equal, when they're all equal, that means the matrix is diagonalizable. Okay, and so in order to diagonalize, so now that the problem says if it is, determine whether or not it is, which determines it is. If it's diagonal, find the matrix P that diagonalizes A and find P inverse AP. Okay, so now we just want to, so to diagonalize a matrix, we just want to find a basis for each eigenspace, but we basically did that already. So a basis for this eigenspace is generated by T. So the basis is let me just put the basis for this one is 0, 1, 1. The basis for this one is the basis for this next one, right down here. They run out of room. The basis for this one is x1 is T, x3 is S. So that means you have x1, you have x1, x2, x3 is equal to T so x2 is equal to, by the above, it's equal to 2x3 or 2s. So x2 is equal to 2s and x3 is equal to s. So this is equal to T times 1, 0, 0 plus s times 0, 1, 1. And so now we can make the matrix P that orthogonally that diagonalizes A as being using the basis vectors. And so our basis vectors are 0, 1, 1, 1, 0, 0, and 0, 1, 1.
Isn't it supposed to be 0, 2, 2 for the S part on the bottom?
It might be. Okay, x3 is equal to, oh wait, x3 is, no, wait, x3 is equal to S because it's its own parameter. X1 is equal to T, that's fine. X2 is equal to 2S, no, that's fine.
Yeah, I mean the part on the bottom where you write like x1 equals, x2 equals, x3 equals.
Oh, right. Good. Yep, there it is. Okay, I knew, you have to get different vectors. It can't be the same. Okay, so this is 0, right? That would, it can't be the same as the other first column. Okay, so this, thank you. Okay, so this is 0, 2, 1. Very good. Okay, so now that is a matrix P that orthogonally diagonalizes the matrix. P inverse AP, it depended on the order of the columns I chose. So the columns I chose, the first column corresponded to lambda equals 1, and the second and third columns corresponding to lambda equals 2. And so P inverse AP, which is the diagonal matrix, is that one. And that's it, okay? And so now we got P inverse AP, we got P. And so that's the problem. That's the entire exam, okay? The entire practice exam. Okay, so I'm going to now save the whiteboard. Okay, and that's it. Okay, I have to go. So I will see all of you on Thursday, and good luck studying. Okay, bye. Good night.